Welcome to the deep dive. Today we're exploring what feels like one of the final frontiers of AI efficiency.
Yeah, it's a big one.
It's about how to get these huge AI models to process human speech without, just drowning in data.
A tidal wave of audio data.
Exactly. I mean, think about it. A single second of good audio has thousands of data points.
Right, and if you try to feed hours of that raw waveform into a model, the cost, it's just staggering.
So our mission today is to understand a research framework that offers a really revolutionary shortcut.
And this isn't just about simple compression.
No, it's about creating a hyper-efficient, what they call a neural tokenizer.
A tokenizer that transforms continuous speech into this highly concentrated stream of data tokens.
Tokens that carry all the linguistic meaning, but, well, none of the acoustic baggage.
And we're diving into a two-stage architecture that pulls this off. It combines the predictive power of JEPA, the Joint Embedding Predictive Architecture,
With a new innovation called Density Adaptive Attention Mechanisms, or DAM.
Right. The whole point is to produce these robust semantic representations that let us dramatically compress voice into a vocabulary that LLMs can actually handle.
So we're basically decoupling the two biggest challenges here.
That's the core idea. Learning what the speech means is separate from reconstructing the sound.
And our source for this deep dive is a really comprehensive paper on it titled JEPA as a Neural Tokenizer, Learning Robust Speech Representations with Density Adaptive Attention.
To really appreciate what they're doing here, you have to understand the fundamental conflict they're trying to solve.
Okay.
For decades, traditional speech coding systems, codecs, have had this major architectural handicap.
That sounds like that classic trade-off we always see. Clarity versus file size.
It is, but in the context of AI, that trade-off costs us something much bigger.
Which is?
It costs us purity of purpose. The training for older speech encoders, it conflates two totally distinct goals.
Okay, what are the two goals?
So goal one is semantic, learning high-level representations that capture the meaning, the words.
What's being said?
Exactly. And goal two is perceptual, preserving enough low-level detail so the audio sounds clean and natural on playback.
Ah, I see the problem.
Yeah, when you try to train a single encoder to do both jobs at once, it's forced to prioritize the low-level waveform details. It becomes a slave to making the sound perfect.
So it's obsessing over the exact shape of the waveform, the tiny harmonics and noise.
Right. And because of that, it gets much worse at extracting the high-level, generalized meaning that we actually want for downstream AI tasks.
It's like trying to write a great novel while also obsessing over the ink saturation on every single page.
That is a perfect analogy, and that's why the beauty of this JEPA framework is the separation of concerns.
So how does it separate them?
Stage one is purely about content. The encoder is trained only with JEPA's self-supervised method. It learns to predict mask representations in the latent space.
So it's only optimizing for semantic content. It doesn't care at all about how it sounds.
Zero attention to waveform reconstruction. That comes later.
In stage two.
Correct. A completely separate decoder is introduced in stage two to map those robust semantic representations back into high-fidelity audio.
So that decoder is the one focused only on reconstruction quality.
Exactly. And that separation means the stage one encoder produces these pristine, flexible, robust representations for any task that needs understanding.
And that flexibility, that's key. The encoder can now be this universal tool for text-to-speech, voice conversion.
Even zero-shot speaker ID, because its output isn't polluted by low-level acoustic junk.
And what about scalability?
Critically important, because stage one is self-supervised, it just needs audio, no transcriptions, so it can use immense amounts of unlabeled data.
Like the data set they use.
Yeah, they pre-trained the encoder on the colossal Librelite corpus. That's around 9,000 hours of speech.
9,000 hours. That's massive. And that kind of scale is what you need for truly generalized representations.
It is.
Okay, let's talk about the architecture then. How does this encoder manage to strip away so much redundancy so early on?
It uses a pretty sophisticated design, a convolutional transformer hybrid.
Hybrid?
Yeah, the raw waveform first goes through several conv1d blocks for initial feature extraction and downsampling.
And then that feeds into the transformer part.
Right, into 8 powerful conformer layers. And this progressive downsampling is the secret to their massive early compression.
Which leads to that remarkable frame rate.
It does. By the time the features leave the encoder, they've achieved a really sparse latent frame rate of approximately 2.5 hertz.
2.5 hertz. So just to be clear, that means it's only generating a new frame of representation every 400 milliseconds?
Precisely.
That's incredibly sparse. Which brings up a big question. How do you make sure those few frames actually carry meaningful, concentrated content.
Excellent point.
I mean, if you're throwing away 99% of the data, how do you know the 1% you're keeping is the important part?
And that brings us to the mechanics of JEPA itself.
The learning mechanism in stage 1.
Right. So JEPA is a self-supervised method. It uses two parallel pathways. You have the online encoder.
That's the network that's actually being trained with gradient descent.
Correct. And then running alongside it is the target encoder. It has an identical architecture, but it provides stable targets for the online encoder to aim for.
And its parameters are updated very slowly.
Very slowly, using an exponential moving average, or EMA. The slow update is what gives the process stability.
So the goal isn't just copying the input. It's about the online encoder guessing what the stable target encoder would have produced in the hidden parts of the audio.
That's it exactly. They use a mean squared error loss, but, and this is key, they only calculate that loss on the regions that were masked out.
Which forces the model to learn context, to fill in the blanks.
Just like a predictive text engine learns language.
And the masking strategy here seems critical. They're not just hiding random points.
No, it's block-based temporal masking. They create these contiguous masked spans, which forces the model to learn deep, long-range dependencies.
And they're pretty aggressive with it.
Very. A ratio of 0.5, so 50% of the input speech is just hidden. The model really has to work for it, which builds much stronger representations.
Okay, so this is where the really big architectural innovation comes in. The Density Adaptive Attention Mechanism, or DAM.
Yes.
Why do you need a new attention mechanism when standard self-attention has basically powered this entire revolution?
It's a great question. Standard self-attention is phenomenal at finding correlations. It asks, which time steps are similar to this one?
Okay, so it maps similarities.
Right. DAM does something conceptually different. It computes statistical salience.
Statistical salience. So standard attention sees similarity, but DAM sees novelty.
That is a perfect way to put it. It's like a statistical editor.
Flagging the parts of the speech that are unusual or unexpected.
Exactly. It looks for the statistical anomaly, the part of the signal that carries the most information, the most surprise, and forces the model to pay more attention there.
How does it actually spot that?
It operates by tracking temporal statistics, specifically the mean and variance of the features over time. Then, it uses these learnable Gaussian mixture distributions to model the expected statistics.
And if a region of audio deviates from that expectation,
It computes an attention gate. This gate scales the full feature tensor, basically shining a spotlight on the most informative regions for the predictor to focus on.
which makes the whole learning process way more efficient. The model isn't wasting time predicting redundant stuff, like a long sustained vowel.
And we have clear evidence of that. In the paper's training loss comparison, the model with DAM converged much faster and got a significantly lower final loss.
What are the numbers?
It plateaued around 0.09. The version without DAM struggled and stalled out around 0.17, so DAM literally halved the prediction error.
Okay, so stage 1 gives us these robust, semantically pure, compressed features. And now we move to stage 2, turning those continuous features into discrete tokens for an LLM.
Yep, the focus shifts entirely to tokenization and compression. And the technique they chose is called finite scalar quantization, FSQ.
Why FSQ? We hear so much about VQ, VAE in these complex, learned codebooks.
And that's the advantage right there. FSQ is computationally way simpler because it doesn't need a learned codebook.
So it's not learning a library of sounds.
No, it just uses fixed scalar quantization. Think of it like snapping a continuous value to the nearest tick on a fixed 4-level ruler.
Okay.
Their specific setup uses 4 levels on 4 dimensions, operating on a code dimension of 128. This gives you 128 indices for every one of those 2.5 hertz frames.
Right, 128 indices every 400 milliseconds. But how do we get to that headline number, that incredibly low token rate of under 50 tokens per second? You have to compress those 128 indices.
And that's the genius of the compression trick. Mixed radix packing.
Mixed radix packing.
It's a mathematically perfect way to squeeze those 128 indices into as few fully reversible tokens as you can.
How does it work?
The algorithm takes a group of FSQ indices and combines them into a single compact integer token. They chose a group size of 7.
So it takes 7 of those 4-level indices.
And combines them using powers of 4 into a single integer.
Okay, so 7 indices, each with 4 possible values.
Exactly. The total vocabulary size for one of those packed tokens is 4 to the power of 7, which is 16,384 unique codes.
And that vocabulary size is crucial. It's comparable to what you'd see in NLP with subword vocabularies.
Making it instantly familiar to text-based LLM.
And the grouping is where the efficiency really multiplies. They have 128 dimensions, packed in groups of 7. That gives you 19 groups per latent frame.
And since the frame rate is 2.5 hertz, you just multiply 2.5 by 19 groups per frame.
And you get the final token rate, 47.5 tokens per second.
A staggering number.
47.5. I mean, for perspective, codecs like SoundStream or encodec, they often run at 75 tokens per second, or even higher, just to maintain sound quality.
And this system is delivering all the semantic content at nearly 2/3 the rate.
And it's perfectly reversible.
Perfectly. The tokens can be unpacked cleanly using modular arithmetic, so the LLM doesn't have to learn compression, it just handles the compact tokens.
Which brings us to the final stage, reconstruction. Turning those tokens back into a high-fidelity waveform.
For that, they use a well-established standard, the Hi-Fi Jan decoder. It's excellent at generating realistic audio.
And since stage 2 is all about perceptual quality, the loss function must be pretty complex.
Oh, it's a multi-objective juggernaut. You've got your standard L1 reconstruction loss for waveform accuracy.
That also.
Also, a multi-resolution STFT loss, which prevents those annoying warbling artifacts, and a strong adversarial Jan loss, which really pushes the audio quality towards realistic human speech.
And the whole system, the final inference model, comes in at about 191 million parameters. It's a powerful system, but it's designed for speed.
But before we wrap up, we should probably touch on the current limitations. What hasn't this solved yet?
Well, I noticed they mentioned the masking strategy. Block masking is good, but it's fixed.
Right.
Wouldn't an adaptive masking strategy, one that's sensitive to linguistic boundaries like words or phonies, be even cleaner?
Absolutely. Making the masking adaptive is a clear next step. They also note the evaluation is entirely limited to English.
On the Liberalike corpus.
So generalizing to tonal languages or morphologically rich languages, that's going to need more testing.
But the promise of extending this architecture, especially to cross-modal JEPA, is huge.
Imagine using this to predict audio from visual cues or audio from text. That's where you get into true multisensory AI grounding.
So what does this all mean for you, the listener? This research successfully validates a pure, self-supervised approach, JEPA, enhanced by this DAM mechanism to create robust semantic speech representations.
And that robust representation gets married to a stage 2 breakthrough using FSQ and mixed radix packing to achieve exceptional reversible compression.
The result is a highly efficient speech tokenizer. It delivers linguistic meaning to language models at that dramatically low rate of 47.5 tokens per second, making speech processing faster and cheaper than ever before.
Indeed. We know that semantic content, while keeping reconstruction possible, can be captured at 47.5 tokens per second. But here's the provocative thought to leave you with.
Okay.
If we throw out the requirement for reconstruction entirely, if the only goal is pure semantic understanding for, say, transcription.
How much further can this token rate be compressed?
Exactly. Could we get down to 10 tokens per second, maybe even 5, before the underlying linguistic structure is totally lost?
It really makes you wonder about the absolute minimum data density required to transmit and understand human meaning.